My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 387. In this lecture, we will try to understand code sample of support vector machines. If you look at this, there is a very nice page called RBF SVM parameters, which tells us what is gamma here. Here it says clearly gamma is parameter can be seen the inverse of radius of influence. Sigma is considered as radius of influence. Just say this one, what it says. Gamma parameter defines gamma parameter can be seen as the inverse of the radius of influence of sample selected by the model as support vectors, isn't it? Suppose if I have C here, just see, let me analyze this. Yes, just say this one. Suppose if I have C here, C is the same for the first three. What is my C value? This is 10 power minus 2. Here also 10 power minus 2. Here also what is my C value? 10 power minus 2. Therefore, I can say the C is the same for first three diagrams. Here only gamma is changing. Just see, in first case gamma is 10 power minus 1. Second case 10 power 0. Next 10 power 1. What does it mean? My gamma is increasing as you go. If gamma increases, what does it mean? Gamma is increasing. Gamma is increasing means gamma is inverse of sigma. Therefore, sigma is decreasing, isn't it? Because gamma is inverse of sigma. Suppose if you have two classes of points, red and blue. Let me consider have two classes of points, red and blue. And let me say the first one. What is the first diagram? What it indicates? Just see. Here I have blue points. This is one class. This is one class, blue points. This is another class, red points class, isn't it? You have two sets of points. If you have small gamma, your decision surface becomes this. What is the decision surface here? This is my decision surface. Just see. This side I have blue points. This side I have blue points. This side I have red points. All these points are declared as blue. All these points are declared as red, isn't it? What is the decision surface? The decision surface which separates blue points and red points. Remember, this is the RBF kernel, but as gamma increases, in other words, as sigma decreases, your surface changes all these points. Just see here, what is your value of this one? Just let me check. As anyway, C is constant, gamma is increasing, isn't it? Here, what is gamma? In first diagram, 10 power minus 1. This is 10 power 0. What is happening here? Your surface changes. All these points are blue. These points are blue points. These points are red points. What is the difference between this diagram and this diagram? Your gamma is changing. Gamma is increasing, isn't it? Now, rest of the points, what is this? And all these points are blue points. All these points are red points, isn't it? Rest of the points, some of them are blue and some of them are red, isn't it? Yes. But as gamma increases further or sigma reduces further, it gets tighter and tighter, literally overfitting. Just see here, it's tighter and tighter. Literally, it's overfitting. Tighter and tighter, isn't it? Yes. I will repeat. What's happening here? Here, gamma, but as gamma increases further or sigma reduces further, it gets tighter and tighter, literally overfitting. This is overfitting, isn't it? This is overfitting. As sigma reduces in the RBF kernel, it is literally overfitting. This is exactly behaving when you have k equal to 1, isn't it? Let me say it is just similar to k equal to 1, or k becomes very small. This is very similar to what happens to what happens to sigma reduces in RBF? They both are equivalent. Sigma reduces or k small value in Knn. This is what happens when you fix C. In this case, we fixed C. Just see, we are fixing C but increasing gamma. In what happens as I am keep on increasing gamma, sigma reduces. Ultimately, it is overfitting, isn't it? Yes, that's what happens when you fix C. When C changes means what? Because remember what happens when C changes, as C increases, it overfits. Just see here, what is C value? In this case, C value is just see like this. Gamma is fixed 10 power minus 1, 10 power minus 1, 10, but you are increasing C 10 power minus 2, 10 power 0, 10 power 2, isn't it? As C increases, we are going to overfit. As C increases, we are going to overfit. As you go down, this C is increasing. Instead of having linear model, your model is changing. Its shape is becoming more and more complex. Just see the shape. Here how you are getting shape. The shape is more and more complex shape. You are getting more and more complex this. There is a chance for overfit as C increases. If I make C instead of 10 square, here we are keeping C equal 10 square. If I keep C equal to, instead of 10 square, if I keep 10 equal to 10, what happens? If I make it 10 power 10, it will overfit like crazy, isn't it? For 10 square itself, you are getting complex surfaces. This is very nice diagram with RBF SVMs, how things change as gamma or sigma and C changes. Remember, always remember, what is your gamma? Your gamma equal to 1 by sigma, and you get all of this nice documentation in this page. Just say scikit-learn RBF parameters. There is also one more support vector classifier, that is new SVC. We already discussed this one. The only difference here, new instead of C. Just see here, you have new parameter. Earlier we had C parameter, here you have new. We already discussed what is new. The only difference here, new instead of C. Here you have C, as we discussed earlier, new controls the number of errors. In soft SVM we were saying C, here we are saying new. What is the purpose of new? It controls number of errors and also its lower bound on the number of support vectors, and everything else mostly that's other parameters almost same. Similarly, you have support vector regression. There is another one, SVR support vector regression, which is already implemented in scikit-learn. The key important factor here is epsilon, because epsilon tells what is the maximum error we can make, because epsilon is nothing but yi minus w transpose xi plus b less than or equal to epsilon w transpose xi b minus y less than or equal to epsilon. Epsilon is greater than or equal to 0. Remember, these constraints in support vector, these are the constraints in support vector regression. So epsilon tells us how much can my y cap be differ from my yi, isn't it? Yi cap, this is yi cap. How much it can be differ? This is yi cap. This is yi, isn't it? This is yi cap. This is yi, isn't it? How much it can be differ? What is the gap between my yi and yi cap? Here again you have RBF kernel, and everything is similar to SVC except epsilon part. Epsilon is the key part, because this is the differentiating factor in the formulation of support vector regression. There is one more very important point. I told you earlier, the best library. What is this best library? Just let me show. The best library, I told you earlier that the best library for support vector missions is libsvm. Just see, this is my libsvm. This is my lib. Where is my libsvm? The implementation is based on libsvm, isn't it? Yes, I will repeat. There is one more very important point I told you earlier. The best library for support vector missions is libsvm. Actually, the implementation here based on libsvm, the implementation of scikit-learn, SVC, SVR is based on libsvm. But those of you are interested to explore libsvm, You just Google search for it, and there is a very nice documentation and code samples on using libsvm. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.